so we are continuing on page 217, and we are in part 7 of biostatistics. Intention to treat and per protocol analysis. Data from clinical trials can be analyzed in two different ways: intention to treat or per protocol. Intention to treat analysis includes data for all patients originally allocated to each treatment group, active and control, even if the patient did not complete the trial according to the study protocol. For example, due to non-compliance, protocol violations, or study withdrawal. This method provides a conservative, real-world estimate of the treatment effect. A per-protocol analysis is conducted for the subset of the trial population who completed the study according to the protocol, or at least without any major protocol violations. This method can provide an optimistic estimate of treatment effect, since it is limited to the subset of patients who were adherent to the protocol. Non-inferiority and equivalence trial designs. The standard design of most trials is to establish that a treatment is superior to another treatment. The researcher wishes to show that the new drug is better than the old drug or a placebo. Perhaps a new treatment is developed that is less expensive or less toxic than the standard of care. Researchers would hope to demonstrate that the new drug is roughly equivalent or at least not inferior to the standard of care. Two types of trials are used for this purpose. So we have the equivalence and the non-inferiority trials. Equivalence trials attempt to demonstrate that the new treatment has roughly the same effect as the old or reference treatment. These trials test for effect in two directions: for higher or lower effectiveness, which is called a two-way margin. Non-inferiority trials attempt to demonstrate that the new treatment is no worse than the current standard based on the predefined non-inferiority delta margin. The delta margin is the minimum difference in effect between the two groups that is considered clinically acceptable based on previous research. Page 218. Forest plots and confidence intervals. Forest plots are graphs that have a forest of lines. Forest plots can be used for a single study in which individual endpoints are pooled or gathered together into a composite endpoint. We're going to take a look at the figure below on page 218. More commonly, forest plots are used when the results from multiple studies are pooled into a single study, such as with a meta-analysis. Forest plots provide confidence intervals for difference data or ratio data. Interpreting forest plots correctly can help identify whether a statistically significant benefit has been reached. When interpreting statistical significance using a forest plot, the boxes show the effect estimate. In a meta-analysis, the size of the box correlates with the size of the effect from the single study. Diamonds at the bottom of the forest plot represent pooled results from multiple studies. The horizontal lines through the boxes illustrate the length of the confidence interval for that particular endpoint in a single study, or for the particular study in a meta-analysis. The longer the line, the wider the interval and the less reliable the study results. The width of the diamond in a meta-analysis serves the same purpose. The vertical solid line is the line of no effect. A significant benefit has been reached when data falls to the left of the line. Data to the right of the line indicates significant harm. The vertical line is set at 0 for difference data and at 1 for ratio data. Comparing difference data. The study shown to the right, which is a meta-analysis by Miller et al., uses a forest plot to test for significance with difference data. Recall for difference data, a result is not statistically significant if the confidence interval crosses 0. So the vertical line, the line of no difference, is set at 0. Examples for high dosage vitamin E. Third study shows a statistically significant benefit, and the benefit point plus the entire confidence interval is to the left of the vertical line and does not cross 0. In the fifth study, the result is not statistically significant and the confidence interval crosses 0. In the ninth study, we have data showing a statistically significant harmful outcome. The data point plus the entire confidence interval is to the right of the vertical line and it does not cross 0. Continuing to the bottom of page 218, comparing ratio data. The study shown to the right by Pogue et al. Uses a forest plot to test for significance of a composite endpoint reported as ratio data. In this case, hazard ratio. So recall for ratio data, the result is not statistically significant if the confidence interval crosses 1. So the vertical line, the line of no difference, is set at 1. Here are the examples. There's a primary composite endpoint. A statistically significant benefit was shown with treatment. The confidence interval 0.7 to 0.99 does not cross 1, and the horizontal line representing the confidence interval does not touch or cross the vertical line at 1. Cardiovascular death. This endpoint shows no statistically significant benefit or harm. The confidence interval is 0.92 to 1.83. It does cross 1, and the horizontal line representing the confidence interval crosses the vertical line at 1. All right, let's move on to page 219. We're going to review the types of medical studies. So we have a pyramid, and on the bottom of the pyramid we have expert opinion. Above that we have case series and case reports. Above that we have case-controlled studies. Above that we have, in terms of reliability, we're going up in terms of reliability from least reliable to most reliable, so the pyramid narrows. So case-controlled studies, cohort studies, randomized controlled trials, and then the top, very top, is systematic reviews and meta-analyses. So evidence-based medicine, EBM, which is largely guideline and protocol driven, is the foundation of practice, and most patient care recommendations are based on valid study data. The type of study that a researcher chooses is a major factor in determining the quality of the study data and the clinical value or impact. The pyramid figure, again on the right, depicts the reliability of each of the major study types. So let's see, we had our case-controlled study, which was, these are located in the middle of the pyramid. Case-controlled studies can be retrospective comparisons of cases, like patients that have a disease, and controls, patients that don't have the disease. Above that is cohort studies, so this can include retrospective or prospective comparisons of patients with an exposure to those without an exposure. Above that, we have our randomized controlled trials. So this can include prospective comparison of patients who were randomly assigned to groups. And then above that, we have the best and most reliable data, which would be the meta-analyses. And this can include analyzing the results of multiple studies together or systematic reviews. So each type of study has benefits and limitations, and we're going to go through the following tables to describe the various study types and provide an example of each study.